So, picking up from our discussion on the scientific and phenomenological traditions, let's now turn our attention to a specific intellectual current that has profoundly shaped modern thought about the mind: cognitivism. Our journey begins with its foundational ideas, tracing back to the vibrant, somewhat chaotic era of cybernetics. Think of it as the intellectual Wild West of the mid-20th century. The big idea taking shape here is that the mind isn't just some fuzzy feeling or ghost in the machine, but something more like a computer program running on the brain's hardware. The pioneers, like McCulloch and Pitts, were incredibly bold. They proposed that neurons aren't just firing randomly, they're performing logical operations, acting like tiny switches in a vast circuit. It was a radical leap, suggesting the brain itself is a physical embodiment of logic, a deductive engine. This wasn't just philosophy, it directly influenced the birth of digital computers and set the stage for what would become cognitive science. Now this cybernetics phase was incredibly fertile ground. You had engineers, biologists, mathematicians, psychologists all talking to each other, throwing around ideas like logic, information, control systems. It produced amazing results, from early AI concepts to systems theory influencing everything from economics to ecology. But, as often happens when a field is young and exploratory, it got messy. To really establish itself as a proper science, cognitive science had to do some hard work. It needed to cut out some of the fuzziness, to define its core principles more clearly. Think of it like moving from a sprawling, beautiful garden cloud to a meticulously planned, structured landscape crystal. This process of clarification happened around 1956, when figures like Simon, Chomsky, Minsky, and McCarthy started formalizing the core idea into what we now call cognitivism. The focus shifted from the broad interdisciplinary spirit of cybernetics to a specific, testable hypothesis about how the mind works. So, what exactly is this core hypothesis? At its heart, it's a powerful analogy. Intelligence, whether human or artificial, looks a lot like computation. We can define cognition as computation performed on symbolic representations. Let's break that down. Computation is manipulating symbols according to rules. Representations are crucial. They're the mental equivalent of words or pictures, things that stand for something else in the world. This brings us to intentionality, the philosophical term for aboutness. The key insight is that intelligent behavior implies you're representing the world somehow. If your representation is accurate, your actions will likely succeed. Simple enough, right? Well, the controversial part comes next. Cognitivism takes this a step further and claims that the only way to explain intelligence and intentionality is by assuming these representations are physically realized as a symbolic code inside the brain or a machine. It's not just metaphor, it's a literal claim about the underlying mechanism. Okay, so if the mind is a computer, how does it actually work? How do beliefs and desires translate into physical brain states? This is the classic mind-body problem, reframed through the lens of computation. The cognitivist answer hinges on symbolic computation. Imagine symbols as physical tokens, like words on a page, but with inherent meaning, semantics. Computations are the rules for manipulating these tokens. Crucially, these operations aren't arbitrary. They respect the meaning encoded in the symbols. That's why the slogan, "No computation without representation," makes sense. Now, think about a digital computer. It doesn't understand the meaning of the code it runs. It just manipulates the physical bits. However, its operations are constrained by the programmer, who built the syntax to reflect the desired semantics. Cognitivism argues this parallel shows how intentionality, the semantic aspect, could be physically realized through computation. The brain, like a computer, manipulates physical symbols whose structure reflects their meaning. This leads to a really important point, a cornerstone of cognitive science, the idea of multiple levels of explanation. Cognitivism doesn't just say the brain is a computer. It posits that understanding the mind requires looking at different levels beyond just the physical brain tissue. First, there's the symbolic level. Think of it as the language of thought. While these symbols are physically implemented in the brain, the level of symbols itself isn't reducible to the physical details. Why? Because the same symbol, say the word dog, could be represented by different patterns of neural activity in different people, or even in the same person at different times. Second, there's the semantic or representational level. This is about the meaning, the concept of a dog. Again, this level isn't reducible to the symbolic level. The concept dog could be represented by different symbols in different languages or cognitive architectures. So, cognitivism gives us at least three levels: the physical brain, the symbolic system running on it, and the semantics of those symbols. This multi-level view is a major innovation, providing a framework for understanding complex phenomena. Now, this computational model brings up a tricky issue, especially concerning syntax versus semantics. In a computer program, the programmer deliberately designs the syntax, the code structure, to reflect the semantics, the meaning. It's a top-down imposition. But does the same hold true for human language and cognition? Can every meaningful distinction we make be neatly captured by some syntactic rule? Philosophers have long argued against this possibility. Think about Searle's famous Chinese room thought experiment. Can a system truly understand meaning just by following syntactic rules? And crucially, where does the meaning in our own mental symbols come from? Unlike a computer where the programmer injects meaning, the cognitivist hypothesis suggests our brain's symbols get their meaning somehow intrinsically. This raises the fundamental question: how can a system based purely on manipulating physical forms, sex, ever generate genuine understanding or meaning semantics? It's the Achilles heel of the purely computational approach. So where do we see this cognitivist idea put into practice? Two main places stand out. First, artificial intelligence. AI is essentially the most direct application of the hypothesis. If the mind is computation, let's build a machine that computes. The whole goal of AI, from early expert systems to modern robotics, is to create systems that exhibit intelligent behavior by processing symbolic representations. A great example of this ambition was Japan's fifth-generation computer project back in the early 80s. This wasn't just a lab project. It was a massive national initiative aiming to build machines capable of understanding natural language and even writing their own programs. Their chosen weapon: logic programming, specifically the language prologue. This project really highlighted how deeply intertwined the theoretical ideas of cognitivism were with the drive to build intelligent machines. The other major manifestation is within psychology and neuroscience. Cognitive psychology, unlike Freudian psychoanalysis, which we'll touch on later, embraced the cognitivist framework. Instead of treating the mind as a black box, it used tools from computer science to study mental processes. Mental representations became the key construct, seen as manifestations of formal systems. The mind's activity, like belief or desire, was understood as infusing these representations with specific attitudes. Interestingly, while psychology looked inward, it heavily influenced neuroscience, often implicitly. The cognitivist view dominates how we think about the brain today. Consider Hubel and Wiesel's work on the visual cortex. Finding neurons that respond to specific features like lines or edges seemed perfect proof for the cognitivist idea. The brain processes visual information step by step, from simple features to complex objects. Some went further, like Barlow with his infamous grandmother cell hypothesis. The idea that a single neuron might represent the concept of your grandmother. Though less popular now, the core idea of the brain as an information processing device remains central. To appreciate the impact of cognitivism, it helps to remember where psychology was before. After the failures of introspectionism, which couldn't agree on anything because people introspected differently, behaviorism took over. Its motto was: the behavior is the data, the mind? Unobservable, irrelevant, a black box. Stimuli come in, behaviors go out. That's all the scientists needed to know. Then, in the late 50s, cognitivism arrived like a breath of fresh air. Early researchers found clever ways to indirectly measure mental processes. Take mental imagery. A behaviorist would dismiss it as unobservable. But experiments showed that holding a mental image, like a letter F, made you slower at detecting another F visually. Proof. It was a measurable effect. The computer metaphor was liberating. Suddenly, psychologists could talk about internal representations, rules, and computations again. Things behaviorism had banished. Common sense ideas, like children learning language by forming hypotheses or motivation being about pursuing goals, could finally be discussed scientifically. But this liberation also sparked debate. Take mental imagery again. Those experiments showing mental images rotate in real time, just like perceived objects? This troubled strict cognitivists. How can manipulating abstract symbols produce such continuous perceptual-like experiences? Some, like Pilishin, doubled down, arguing imagery is just a side effect, an epiphenomenon of deeper symbolic processing we don't consciously access. Others, like Koslin, tried hybrid models, suggesting both symbolic and image-like operations interact. The debate continues. Another interesting intersection is with psychoanalysis. Interestingly, Freud himself was quite cognitivist in his thinking. He believed everything affecting behavior had to go through a representation. His unconscious wasn't anti-representational, it was just a different system of representations. Later thinkers tried to translate Freudian concepts like repression into cognitivist terms, like pattern matching algorithms filtering unacceptable thoughts. While useful for comparison, critics argue this misses the deeper psychoanalytic point about transcending representation altogether. Now, let's get to some really profound implications of cognitivism, particularly for our understanding of consciousness and the self. Dennett famously called cognitivism a theory of the subpersonal level. What does that mean? It means cognitivism explains our behavior using mechanisms that operate below the level of our conscious awareness. Think about reading a sentence. Are you consciously aware of the grammatical rules or the dictionary definitions being accessed? Probably not. These processes happen subpersonally. This is a big deal because it challenges our usual understanding of the unconscious. Freud thought the unconscious was hidden but potentially accessible through therapy. Cognitivism, however, suggests some mental processes might be fundamentally inaccessible, perhaps even modular, meaning they operate independently and cannot be overridden by conscious thought. This directly challenges our intuition that consciousness is central to being a mind. This leads to an even deeper puzzle. What is the self? If cognition happens largely unconsciously, and consciousness itself isn't essential for cognition, then what holds our mental life together? We all feel like there's a unified I experiencing the world, making decisions, having thoughts. But if you look inside the brain according to cognitivism, you find a collection of specialized, often unconscious, processes. Dennett captures this beautifully. Imagine entering your brain, looking behind every neuron, and suddenly popping out, scratching your head, wondering where the self is. It's like searching for a homunculus inside the head. But the cognitivist challenge goes deeper than just saying we can't find the self. It questions whether the self is necessary at all. If cognition works perfectly well without it, why do we have this persistent, powerful sense of a unified self? How do we bridge this gap between the unconscious computational mind and our conscious experience? Enter Ray Jackendoff. He calls the problem the mind-mind problem. How does the computational mind relate to the phenomenal mind, the world of conscious experience? His proposal is elegant. Consciousness isn't a separate entity, but rather a projection or externalization of elements from the computational mind. Think of it like this. The computational system generates various representations, and consciousness selectively presents certain intermediate-level representations to our awareness. These aren't the raw sensory inputs, nor are they the high-level abstract concepts. They're representations in between. This idea has two big consequences. First, it means computational theories must account for the structure of conscious experience. Phenomenology isn't just philosophy, it's empirical data that constrains our computational models. Second, it implies consciousness itself is disunified. Just as we have different types of consciousness, seeing, hearing, feeling, Jackendoff argues these arise from different computational structures, reflecting the fragmented nature of the underlying system. Jackendoff's view, however, leads to a rather uncomfortable conclusion, one he himself admits is unpleasant. If consciousness is just a projection, if it doesn't causally influence the computational processes, then what's its purpose? If it doesn't cause anything, it serves no purpose. This brings us face to face with the ultimate question. If cognition can function perfectly well without consciousness, and consciousness itself seems to be an epiphenomenon, why are we conscious? Why this rich, subjective experience? Some scientists seem willing to shrug and say, too bad for experience. Others simply accept it, without questioning its place in the theory. But, is there another way? Perhaps the path forward lies not in ignoring experience, nor in treating it as irrelevant, but in developing a disciplined, open, and direct investigation of experience itself. This sets the stage for exploring traditions like mindfulness and open awareness, which offer potential paths to understanding the very experience that cognitivism struggles to explain.